Professor.
Yes.
So the final exam is from 1 to 3 Mountain Daylight Time.
Yes,
right?
yes, our time. Yep.
Okay.
If
Because I'm in Arizona, so it's an hour earlier.
Oh, you gotta be
12 to 2,
yeah.
right? Okay.
I think so. I'm challenged with time zones because I grew up in a single time zone place, so this time zone thing is confusing to me. But yes, so make sure you it is Mountain Time. Okay.
Okay.
It is Mountain Time. Yeah, thank you. Okay. All right. So last time we did a boundary value problem. It had a kind of benign right-hand side. It was a heat transfer in a rod, and we understood how we discretized that, converted at each, discretized this into points, discretized the rod into discrete points, and then converted the continuous ordinary differential equation into an algebraic relation that relates, you know, the unknown temperature at one point to the unknown temperature at two other points, but that gave us a system of n equations with n unknowns, n being the number of points, and then we know how to solve that. We can use NumPy solve, etc. That's not an issue. But then we looked at this boundary value problem where I only changed the right-hand side. Previously on the right-hand side, you had something, a function of the temperature t only, not t squared or square root of t or sine t. And then I asked you to discretize this, and you all went ahead and discretized it correctly. But then you observed that the discrete equation at every point is actually a nonlinear equation. So the system of equations that we're going to build is going to be nonlinear in this case. And we discussed that at length last time. But just to remind you, we are trying to solve for ti, for I going from 1 to n, right? And every equation at every point is coupled to all the other points. So you need, they're coupled. So that means you have a system. Okay, so equation 1 needs equation 2 needs equation 3, and so on all the way to the n, point n. But each one of those equations is nonlinear. And I said that if left untouched, this is a very large system of coupled nonlinear equations. Can we solve it using Newton's method for systems of equations? Absolutely. But it is very expensive to do. Okay, so what I'm going to present here to you is the last thing we're going to cover in this class, and that only kind of works for differential equations, and we do this all the time in the research area I work in. We call this source term linearization. Turns out there's a way to embed the Newton solve within the system of equations that we obtain, rather than having to build a Jacobian, and the Jacobian matrix is annoying and huge and is very dense. So rather than having to do that, we kind of circumvent Newton's method and embed it within the solution process. And I'll explain that to you briefly today. It's called source term linearization. When the source term in a boundary value problem is nonlinear, this is what you can do. Now for initial value problems, if the source term is nonlinear, you just use Newton's method, because with a initial value problem, you either have one equation or you have like 4 equations. Even if you have like 50, that's nothing, right? So you just use Newton's method for an implicit method. So remember, with initial value problems, if the right-hand side of the equation is nonlinear, you'll only get a nonlinear equation if the method is implicit. If the method is explicit, it doesn't matter, because you're using values from the previous time step. All right, so for boundary value problems, what I'm going to do here, I'm going to split the screen in 2 portions. On the left-hand side, I'm going to describe the general form, but on the right-hand side, I'm going to do it for a very specific example, which is the one we just described. So in general, if an ODE is given, and I'm giving one specific example here, d2u by dx squared. You could have d2u by dx squared plus du by dx, right? Doesn't matter, you just discretize that as usual, but what matters is the source term on the right-hand side, if it's nonlinear or not. So in general, fxu is nonlinear. And on the right-hand side, I'm giving you a specific example. In this case, the nonlinear source term is alpha t squared, t to the 4th minus t infinity to the 4th. Now, t infinity is a known quantity, so that's not the nonlinear term. The nonlinear term is t to the 4th, okay? That's, it's nonlinear in t, okay? All right, so the first thing we're gonna do, we're gonna start with a guess for the solution for you. Now, this is similar to what we did in Newton's method. We had a nonlinear equation. We would start with a guess for the root and then refine that guess until we hit the root, right? So this is no different. We're going to apply that same method to the equation directly, to the full continuous equation directly. So we're going to assume a guess. It could be the initial condition for the problem or one of the boundary conditions, for example, in this case, could be the boundary condition, one of the boundary conditions, t left or t right, for example. Call it u star. For our example, we're going to call this t star. Then we're going to write the Taylor series of the source term around u star. Now remember, the Taylor series was our preferred method to linearize a nonlinear equation. And that's what we're going to do here. So if the source term in general is f of xu, you're writing the Taylor series around u star. So you're only taking derivatives with respect to u, not with respect to x, okay? Pardon me. So you get fx at u star plus u minus u star df by du. You're differentiating with respect to u, right? At u star and so on and so forth. Now for our specific problem here, specific example, we don't have x in the right-hand side, so our source term is only a function of t, and this would be the Taylor series, and this is going to give you, oh, sorry, I missed one thing here. Okay, now we write the Taylor series, and we're going to truncate at first order. So we're going to keep the zeroth order term and the term that has the first derivative. So those are the first terms that we're going to keep, like we did with Newton's method. And this gives us your first activity. Now I want you to write down the Taylor series for f of t for our specific example. Our example is f of t is alpha t to the fourth minus t infinity to the fourth. So go ahead and write the first two terms in the Taylor series, or up to first order. Okay, you got 2 minutes. Okay, let's see. Katie, since you are in a different time zone, do you have an answer for us?
I believe so.
Okay, go ahead.
Do you want it for the specific example that we're doing?
Yes, for our specific example. Yeah.
So I wrote it down as alpha times t star to the fourth minus t infinity to the fourth.
Correct.
Plus, in parentheses, t minus t star. And then that multiplied by 4 alpha t star cubed.
Excellent.
Minus t infinity.
No, there's no t infinity because t infinity is not a function of t, it's a constant.
Right.
So
that would go to 0.
Okay, so 90% correct. Okay, so what Katie said is correct. We linearize our full source term, which is alpha, over here, alpha t to the fourth minus t infinity to the fourth, by taking the first two terms of the Taylor series. We're committing an error, but we're not going to worry about that because we're only going to approximate, we're going to iterate through this until we find the root. Now, if you haven't seen this already, what I'm trying to do here is, my goal is to refine t star until it is consistent with t, the true solution, or the root of the equation. Remember, our t star is the guess. and t is going to be our actual solution, our actual root. So initially they're going to be different, and you'll see this in a second. But the first step is to take this full source term and approximate it, linearize it. Now all terms are linear because t shows up linearly, and t star is just like t infinity. It's a guess, okay, that we're going to keep refining until we hit a certain condition. So I would typically just simplify the algebra like I'm showing here. So my full source term becomes minus 3 alpha t star to the fourth plus 4 alpha t star cubed times t minus alpha t infinity to the fourth. Again, t is our unknown, okay? And t star is only a guess. That's why there's no nonlinearity over here anymore in terms of t. Everything is linear in terms of t, as long as we know t star, okay? And t star is a guess, and we're gonna refine it. We'll see in a second. Now we substitute into the ODE. So you take the right-hand side that you just derived. Again, on the left, I'm showing the generalization, which I think, you know, could be too much for someone to kind of memorize or reproduce. Just if you follow the steps, linearize the source term, substitute into the ODE, just follow the steps, you'll be able to apply this to any type of ODE, okay? Don't blindly use the general formula, okay? And so we substitute into the ODE, and now I claim that this is gonna be our new ODE that we're gonna be dealing with. Remember, we're still continuous here. We haven't discretized anything. All we did was approximate the source term around some guess t star, okay? Next, we discretize our standard discretization, and that gives us the standard central discretization on the left. And on the right, everything is at point I. Now, there's a trick here, not a trick. There's a subtlety here that t star is not a value across the entire domain like t infinity. Every point in the domain has its own t star. Again, think of t star as the guess for the root of the nonlinear equation at point I. And therefore, every point I has a different equation and therefore has a different root. Therefore, your guess needs to be a vector of guesses, right? Rather than just one guess for the entire one constant value. Every point has a different guess, has a different root, okay? Because it has a different equation, different nonlinear equation, okay? Next, we collect the terms. We put everything we don't know on the left-hand side, all the unknowns on the left-hand side, and everything we know on the right-hand side. It's just algebra. So, you know, if I were you, I would derive these equations at home and make sure that, you know, you collect the terms, everything correctly. So now, pardon me, we actually have a linear system of equations, right? So at point I, the linear equation is given by ti minus 1 minus 2 minus into 2 plus 4 alpha delta x squared, etc. Ti plus 1 minus alpha delta x squared into whatever. Again, our unknowns are ti's, so ti minus 1, ti, and ti plus 1, and that gives you a system of equations, okay? And these equations are linear. So in the general case, I'm showing the matrix on top. Again, don't worry about that. Worry about doing it specifically for a particular problem. So for our particular example, this would be the system of equations. It's just nothing different than what we did before, except we have this annoying t star or u star floating around. Okay, so now we can, given a value for t star, you can solve this system. Agreed? Because the coefficient matrix is known. There's actual values in it. The only unknowns are the ti's, t1 all the way to tn. Okay, but there's this u star everywhere, and we said that u star is only a guess for the true value of u, or t star is the guess for the true value of t, or whatever variable. However, we also know that u star should eventually converge to u. So u and u star need to be the same value, okay? However, when we are starting, we start with a guess u star, and then we solve for u, or we start with a guess for t star, and then we solve the linear system for t. But then they're different, right? U star, t star, and t are gonna be different because in general, you're not gonna be able to guess the true solution directly, right? So what do? We just iterate. So we first start with a guess for our solution, this t star or u star at every point, okay? And then we solve the linear system of equations. Okay, and to solve that, you need to use U star in the coefficient matrix and in the right-hand side. There's U star everywhere. Okay, so you update your coefficient matrix and you update your right-hand side. So this is more programmatic now. Okay, what we do in terms of programming. Then you solve the system of equations for UI, and then you ask yourself, or TI, is T equal at every point? How far away are T and T star? If they're far, what do? You take the T that you solved for and make it your new guess and repeat until they all become close to each other, until U star is close to U or T star is close to T. And then you'd say, well, that's it. My guess and my solution have converged to the same value. And typically, these methods converge all the time because this is another way of doing Newton's method, except we embedded everything in the system of equations, okay, rather than having to do a Jacobian, etc. Okay, and that's it. That's how you do boundary value problems with nonlinear source terms. I know it can be complicated to untangle all of these systems of equations and nonlinear and linear, and I understand, and it takes time. Okay, it takes time to kind of for this to sit in your mind, to stick in your head. But think always about what you're solving for, okay? And over here we're solving for the U's or the T, okay? And T star is only a guess that is given to you initially. You start with that, you solve for T, and then you say, well, my T star needs to be close to T. If they're not close, then I'm going to use my T as my new guess and repeat. Update the coefficient matrix, update the right-hand side, solve the linear system, and repeat and repeat. And in the remaining slides, I repeat this example for you that we kind of just did together. So make sure you go through it, okay? Because this will be on your final exam. So here's a tip for you. There's not going to be programming where you're not going to, in the homework that I gave you, there was a programming question to program this. And the programming this is very easy. You just embed the linear system, which we know how to build. We know how to build the coefficient matrix for this problem. We know how to build the right-hand side. So you embed those in a loop, and you keep looping until T star and T are less than a certain tolerance. And that actually concludes everything I wanted to cover in the course. Typically, I also go over partial differential equations. But we'll see if we have time by the end of the lecture. I'll go over those, but I don't think they should be required in this course at this time. And if you have any questions, go ahead before we get started on our activities. No questions? Okay, let me check the chat. There's no chat. Okay, I'm gonna go ahead and stop the recording because